All right, let's jump right into this absolute mountain of trigonometry formulas. I know, at first glance, it looks kind of like an intimidating alphabet soup of Greek letters and floating numbers. But I promise you, it's not chaos. It's actually just one beautifully connected, master-built puzzle. Welcome to this explainer. We're not just going to sit here and memorize a boring list today, no way. We're going to learn how to read the actual blueprints of geometry. Let's do this.
To keep our brains from completely overloading, we're going to organize this whole thing into 5 clear structural levels. First up, the right triangle foundation. Second, quadrants, circles, and angles. Third, shifting with allied angles. Fourth, sums, differences, and products. And finally, scaling double to half.
Okay, level 1, the right triangle foundation.
So these 6 basic ratios right here, this is your fundamental toolkit. You've got your angle, theta, and your 3 sides, the perpendicular, the base, and the hypotenuse. Sine, cosine, and tangent are your primary tools mapping those sides together. But hey, look at the right column for a second. Cosecant, secant, and cotangent are literally just those first 3 flipped completely upside down. They're just reciprocals, you see? You aren't learning 6 unconnected things, you're just learning 3 pairs of mirrors.
Now, what's really fascinating here is how this Pythagorean identity actually works in practice. Step 1 is the absolute golden rule. Sine squared plus cosine squared equals 1. But look closely at steps 2 and 3. You're not memorizing 3 separate formulas here. You're literally just learning one core truth, and then applying a super simple derivation trick just by moving one piece to the other side of the equal sign. It's like a mathematical puzzle piece.
And this beautifully illustrates how that exact same derivation logic applies to our other functions too. Tangents and secants play together, while cotangents and cosecants play together. Honestly, if you just remember 1 plus tangent squared equals secant squared, well, you get 2 more formulas absolutely for free just by doing some basic subtraction. It is all about efficiency, guys.
Moving right along to level 2, quadrants, circles, and angles.
To navigate this circular map without getting completely lost, we first need to lay down our boundaries using what's known as the ASTC rule. Depending on exactly where your triangle lands as it sweeps around that circle, certain functions are going to be positive and others are going to flip right over to negative.
So the big takeaway here is that as your angle rotates through these 4 quadrants, the functions basically take turns being the positive one. In quadrant I, so 0 to 90 degrees, everybody is positive, all of them. But swing over into quadrant 2, and only sine and its partner cosecant get to stay positive. Down in quadrant 3, that is the territory of tangent. And quadrant 4, that strictly belongs to cosine. A lot of people just remember this whole thing as all sin tan cos. Easy enough, right?
Which brings us to the standard angle values. Now, I know this is a pretty dense table, but it is completely necessary. It maps out our most common, perfect angles between 0 and 90 degrees. But hey, rather than just brute force memorizing this, look at the flow. Check out the top row. Sine climbs steadily from 0 all the way up to 1. Now look at the second row. Cosine does the exact opposite, sliding from 1 right back down to 0. And they perfectly cross over each other at exactly 45 degrees. It's perfectly symmetrical.
Take a quick mental breath here and notice something really cool. The number 1 is the absolute maximum anchor. On that standard chart, sine and cosine never ever climb higher than 1. That one simple number basically frames the entire boundary of our basic trigonometric world.
Okay, before we leave the circle behind, let's look at how we actually measure it. We all use degrees day to day, but mathematicians absolutely love radians. And converting between them? It isn't some complex math. It's literally just flipping the pi over 180 ratio upside down. To get radians, you multiply by pi over 180. To get back to degrees, you just flip it to 180 over pi. Boom, done.
All right, level 3, shifting with allied angles.
So we know our basic angles beautifully now, but we really have to ask ourselves, what happens to these formulas when we start heavily manipulating the angle's position? Like, what if we look at an angle completely backwards? Or what if we look at its exact complement?
Just notice the beautiful symmetry going on here. If you take a complementary angle, 90 degrees minus theta, sine and cosine completely swap identities. Sine turns into cosine, and cosine turns into sine. But look at the bottom row. If you throw a negative sign into the angle, sine passes that negative right to the outside, becoming negative sine. But cosine is a tank. It just absorbs it. Cosine of negative theta is exactly the same as cosine of positive theta. It remains completely untouched.
Moving on to level 4, sums, differences, and products. Now,
When complex geometry requires us to actually combine angle A and angle B, well, simple addition just won't cut it. You can't just say sine of A plus sine of B equals sine of A plus B. Nope, it's an entirely different beast, so we need a very specific set of tools to crack it open.
Look really closely at the pattern here, because there's almost a distinct personality to these functions. Sine formulas kind of play nice, right? They mix sine and cosine together. Notice that sine A, cosine B thing. But cosine formulas? Oh, they stubbornly group the cosines together at the front, and the sines together at the back. And actually, beware the signs. For cosine of A plus B, the formula surprisingly uses a minus sign in the middle. It completely reverses on you.
Let's see how this builds up into our sum to product formulas. If you have two separate sine waves, like sine C plus sine D, and you really want to combine them, these formulas beautifully transform clunky addition and subtraction into super precise multiplication. By taking the average of the angles, so C plus D over 2, and the difference, C minus D over 2, you basically weave two independent waves into one single multiplied expression. It's mathematical magic.
Now, if you place these side by side, it absolutely proves that these advanced formulas are really just two sides of the exact same mathematical coin, just running in reverse. On the left side, we're turning a sum into a product. On the right side, we turn a product right back into a sum. It's essentially unbaking the cake. And honestly, this specific flexibility is exactly what makes trigonometry so incredibly powerful in fields like physics and engineering.
And finally, we've reached level 5, scaling, double to half. When we scale things up by doubling an angle to 2a, the shapes totally transform. Sine 2a neatly unfolds into 2 sine A cosine A. But notice how cosine 2a behaves here. It actually gives us 3 totally different derivation options to choose from. You can use cosine squared minus sine squared, or just write it in terms of cosine, or just in terms of sine. Basically, you get to pick whichever tool best solves the specific problem sitting right in front of you.
And in a quick rapid-fire progression, just see what happens as we scale even further out. Tripling an angle to 3a introduces cubes, powers of 3, but slicing that angle in half, dropping it down to a over 2, that naturally introduces square roots. The math scales in this perfectly logical, entirely predictable direction based purely on the operations we're applying to it.
These final important results basically tie the whole shebang together. Just look at the top 2 bullets there. We take a squared function, like sine squared theta, and we reduce it entirely down into a simple double angle of cosine. We're literally stripping away the exponents, and this proves the entire system is just one big interconnected loop. The absolute highest level of complexity maps flawlessly right back down to our basic shapes. So, the next time you look at this massive list of formulas, I want you to remember, it is not some heavy burden of memorization. It's a beautifully organized, highly logical toolkit just waiting for you to build with it. If every complex wave, from the literal light hitting your screen right now to the sound of my voice, relies on these exact relationships, I'll leave you with this one question. What else in your world is hiding a perfect mathematical pattern just waiting for you to decode it? Thanks for exploring this with me today, and hey, keep your curiosity sharp.